Today's lesson is a big one. It's the laws of logarithms. And log is a Greek word for ratio. Arithmos is a Greek word for number. So this is where we get the word logarithm from. And also arithmetic would come from this word as well. Using the exponent laws from grade 9, we're going to come up with 3 new laws of logarithms today. We've already seen this one, but so I'm just going to kind of recap this one here. For the quotient law, the bases must match to use any of these laws, just like with the exponent laws. For all of our laws, a, that's our base, has got to be greater than 0, can't be negative. Your x and your y also are going to be greater than 0, and a also can't be 1, because a base of 1, well, we talked about that, what that means. Okay, 1 to the power of anything, right? Example 1. Expand. So all I'm going to do right here is I'm going to match it up with my quotient format. So the 4 is what the a is, the 16 is this x, and in this case this x is the same as this y. So matching these up properly, I'm going to rewrite it in this format right here. So base a has got to be, log base a has to be written out twice, in this case log base 4. The x is the numerator, the y is the denominator. That's what we get. The question just says expand. It doesn't say evaluate. Evaluate would mean I'd have to have a final answer like 12. I can't because I have an unknown here. I can simplify this a little bit more. Log base 4 of 16. Now, hopefully many of you now are at the stage where you don't have to write this piece out. You don't have to figure it out. I will just put it on here for you. What you're looking for is 4 to the power of what? Question mark. 4 to the power of what is 16, but I think a lot of you already can do that without having to write it out. So the answer for that piece is a 2. We get 2 minus log base 4 of x. The log base 4 of x, the second part of this expression, cannot be simplified any further. And the question just said expand, so we've done that. We've simplified it as much as we can. We can't go any further. There's nothing, it's not equal to something over here. It's not equal to a number. If this were equal to 10, then I could bring the 2 over and isolate, but it's not, so we leave it like that. Similar one here, simplify. So this one, actually, we are going to be able to evaluate this one, but we're simplifying first, and simplifying, if I just look at log base 5 of 50, and I'm thinking in my head, okay, 5 to the power of what is 50? I can't do that, nor can I do 5 to the power of what is 0.4. But I notice that I have a base of 5 here and here, so I can use my new law. Now I've got, my question is set up in this format, so I've got to revert back to this side here and see if it helps me, and maybe it won't. But right now I can't do anything with, I can't figure this out on my own, I can't figure this out on my own. So I'm going to try to simplify it a little bit. So I'm putting it into the proper format here by matching everything up with this law. Now let's look at the brackets. 50 divided by 0.4. Well, 50 divided by 0.4 is 125. So I can change that to 125. Now can we solve this? 5 to the power of what is 125? So this is one that we should be able to figure out. The answer is 3. So this one we were actually able to evaluate it at the end. And what we have to do, what we are expected to do, what you're expected to do here, I'm going to show you what the laws mean, and we're going to connect the exponential laws with the log laws. So exponents and logs, we're going to tie that together. What you have to be able to do is verify the laws of logarithms with or without technology. So we're going to work through the proofs of these laws. Where does this law come from? You have to be able to verify that law. That means you don't have to figure it out from first principles like I'm going to show you. You don't have to derive it, but you do have to be able to verify it if I gave you part of the formula. I'll explain that more in a minute. And then we use the laws to simplify and evaluate like we just did right here. So this is what we're doing today. First thing we're going to do is prove the product law. We haven't talked about this one yet. So the product law. There are several steps here. The first step with most proofs is to define variables. In order to, I know what my answer has to look like. I want it to look like this when I'm done. So where am I going to start? Now, you wouldn't know this because you haven't really done proofs like this before, but we're going to introduce some variables here. We're going to let a to the power of k equal x. So then converting that to log, we have this form here. So I have this little piece here, log base a of x, there's log base a of x. So I'm trying to get this when I'm done, right? So I'm going to introduce some variables. And we need a y value. If a to the power of m is y, then what is the log equivalent of that? What's the log equivalent of that same thing? It is log base a of what? Of y. And that will equal m. And you'll see why we need this later. Okay. So now try this. If a to the power of n is x times y, then log base a of x times y equals what? I'm converting this to log form here. What goes on the blank line? Remember, the whole point of logs is to access the exponent. So this is equal to n. Next, if a to the power of n is x times y, we already did that. Let me erase this circle I have here. Okay, there. A to the power of n is x times y. We already stated that ourselves. We already have values for x and y up here. Here's x, here's y. We already have values for x and y, and there's my x and y again. So a to the power of n equals, so I'm substituting right here. I've got this little equation here. Now I'm going to put that in for x. So that's a to the power of k is going to go there. That's that a to the power of k right here. And in for y, I'm putting a to the power of m. And using our, as it says, our power laws from grade 9, I've got the same bases that I underlined there in green. So I write the base out once, and because I'm multiplying, I add the exponents, k plus m. So I am going somewhere with this. Actually, we are almost done the proof, although it's very hard for you to tell. Remember what we're doing? We're trying to prove this. We're trying to prove this up here, and it's almost done. And it's just done because of the way we've defined our variables and reorganized them. So that must mean n plus k equals m. Because these bases are all the same, here, remember this is equal to a to the power of n, our bases match. We can ignore them and look at the exponents. That gives us, just like if I had a to the power of 7 equals a to the power of x, well then 7 must equal x. Same thing here, we've got k plus m must equal n. That's this line right here. Now we're going to sub back in with logs. So change colors, let's go to blue. Sub back in with logs here. So this is it. My next line is my answer. Let's start with n. This formula right here, I'm going from here. N, what is n? You see where n is? I'm going to do n first. What is n? Look on the page for n. What is n equal to? Right here. I'm going to write that first. So instead of n, I'm going to put log base a of x times y. And look at that right there at the top. We've got that part done. Now my equal sign is next, equals. Now what's k? Look elsewhere on this page for what k is equal to. Do you see k? K's up here. Let's put a kind of a wavy bracket around this one here, or circle, cloudy thing. So instead of k, I'm going to put log base a of x, which of course matches this one up here at the top. And then my plus sign back down to the bottom, my plus sign. And now m. What is m? Find it on the page. Here it is. I'll put a square box around this one. That's my log base a of m, and sorry, whoops, y, not m, y, and that's up here at the very top. I'm putting the box around the same thing. So that is the product law of logarithms. We've proven that if you have two bases, we're looking at the right-hand side here of the formula, if you've got two logs with the same base and you're adding them, then you can, now I've said this before, it's like you're taking out a common factor of a log A from here and here. That's not what you're doing, but sometimes students like to think of it that way. It's like you're taking that out, and what you're left with are these two that you multiply. And remember, this all goes back to this line right here. I'm erasing these pieces right here in the middle. It comes back to that law that you learned in grade 9 or maybe grade 8. If you have b to the power of 7 times b to the power of 3, that's b to the power of 7 plus 3. If the bases match, we can add the exponents. So it's similar here. When our bases match here and we're adding the logs, we can actually multiply the input pieces here. So that is a proof of the product law of logarithms. And if you remember that expectation I showed you on the previous slide, you don't have to prove it from scratch, but I often I will take this page right here and I will kind of white out a certain part of it or delete it and then ask you to fill it in to see if you can follow the proof. So you don't have to prove it from the beginning, but you do have to be able to verify it. And that's what we're doing here. You're gonna verify it. Now we have another law. This is a really cool one, power law. So just look at this before we do anything. Look at what we have here. This log, so I'll put this first part here in a box, log base a of x, and here's the, log base a of x. Those two are exactly the same. The difference is when we have an exponent, all of a sudden we get to make it a coefficient, a leading coefficient. It is crazy, but it's true, and I'm going to prove it to you, that if you have an exponent, if you have a power with logs, that's the same thing as taking that power, whatever it is, and throwing it up to the front. Okay, seems bizarre, but it is true, and it's a really helpful law to use. First thing, let's get our variables going here. We're going to start with a to the power of m is x, converting that to log form, log base a of x equals m. These two are equivalent statements in different formats. This is exponential, this is logarithmic. And we're doing that because we need to use exponent rules to come up with log laws. So to begin with the power of a power law, remember the power of a power law? That's when you multiply, and I'll just show you a little sample of that. If we had a to the power of 3 to the power of 4, that's going to be a to the power of 12. So these two m and n get multiplied together to be m times n. So here's another strategy that you never would have thought to do before. In the past, you could say, oh, I'm going to multiply both sides by 3, or I'm going to subtract 8 from both sides. That's just basic algebra. What we're going to do is take log with base a of both sides. So here's what that will look like. I just added a log base a onto both pieces. These are the same. I just put a log base a in front of each part. Now simplify the right side right here. Remember from last class, this was one of our kind of special properties. When these two terms, the base and the input, are exactly the same, log base a of a, when these two are the same, do you remember what that's equal to? This piece right here simplifies to something nice. It simplifies to just the exponent mn. And you can go back and look at the last video if you forget how that happened. But this is equal to m times n. So we've got log, this is the same. I didn't change this, I only changed this side here. Now let's look at the left side. Look at the left side. Remember up here what x was? A to the power of m was x. A to the power of m was x. So let's just do that right here. A to the power of m. Put an x in there. I did that in red. So the left side looks good. Look at, we've got our left side of the power law right here. This matches. So we've got this side to work out. Now I need this side to match this side. What can we do? So look at the page. What can we do here? We know what the end result has to be. It has to look like this. The n is already there. We've already got the n there. but there's no m up here. So how can I make this match? Did you see it? It's right here. I'm going to replace the m with this piece, which will match this piece here. Whoops, I should write that down for you, I guess. Let me write that down before we do our next example. That gives us log base a of x to the power of n equals, so instead of m, this m, I'm going to replace it with, I'll put the n at the front, n times log base a of x. That is your power law of logarithms, which is a really easy one and a really helpful one. It just grabs that exponent and throws it down, makes it a coefficient, or you could put it at the end, but it's easier at the front. So let's try this out here. Evaluate. Evaluate means our final answer needs to be a number. There shouldn't be any x's left. First thing I'm going to do is get rid of that radical and change it to an exponent of 1/2. So we have this fantastic new rule that allows us to take the exponent and throw it into the front. Crazy, but it's true, and you just proved that it's true up there. We just proved that we can do that. I'm not making this up. The 1/2 comes right to the front, and that's log base 2 of 8. Okay, log base 2 of 8, you guys should be able to do that. Log base 2 of 8. Again, you can work it out separately if you need to. If you need to write down log base 2 of 8 equals, I pick a letter like r. Okay, so base is 2, exponent is r, equals 8. What does r need to be? It needs to be a 3. So I'm going to go back to my question and put 1/2 times 3. And that's just 3 over 2. And no, you may not write 1.5, 3 over 2. So that's all there is to the power of a power law. Now we're going to do more complicated questions, but that's how helpful it is right there. Example 3, let's use the laws of logarithms to evaluate this one. So this, you've got to find your law that matches what you see here. You're looking at this question, you're looking at your laws, and you're thinking, okay, this one looks like which one here? It looks like the product law. So let's match things up. My bases are the same, so I can write the base once, log base 6, and my input is going to be 4 times 9. That's all. That gives me log base 6 of 36. And again, at this stage, if you want to do some rough work here, you can do some rough work. Log base 6 of 36 equals 6 to the power of a equals 36. That's going to be a 2. That's it. So who would have thought, looking at this weird looking logarithmic expression, that it's actually just equal to the simple number of 2, but it is. Example 4 expresses a single logarithm. So here's some instruction here. We have to put it together as one log first. And of course, we already went over this, all variables are positive. So first of all, expresses a single logarithm. We've got a little hint there what we're supposed to do. So right away, I want to get this 3 up. Now you may not think that. You may think, why, what's the problem with leaving it where it is? Well, there isn't right now, but you'll see it in a second. So I'm going to go ahead and put the 3 as an exponent, x cubed, plus, same thing with this 2. Let's make it an exponent. Log base 4, again, I'm noticing my bases are the same, which is important. Power of 2 minus, and the last term is, I don't have anything I can move around there. Y. The question said expresses a single logarithm. So now I have log base 4. And because I don't have any coefficients in the front, I don't have to worry about them. I've moved them out of the way. I can write my log base 4 once. This is log base 4. Now, the first 2 are going to be multiplied together because of the addition. but then the last input has to be divided. So when I write it out, I'm going to put a bracket here. I've got an x cubed, that was my first input. I multiply that with my next input because that was adding those logs. That's x squared. And then I divide, because my last log is a subtraction, divide by y. And the question set expresses a single logarithm, and we've done that, but you always simplify any further if you can. We can do a little more. We can take those numerators and just put them together. Log base 4 of x to the power of 5 over y. And that's all simplified, and it's written as a single logarithm. So that's as far as that question can go. Example 5. Again, use the law. That's of course what we're doing today, using the laws of logarithms. Express each side of the equation as a single logarithm. So we have an equation this time. We haven't had an equation yet. When you don't have an equal sign in your original question, imagine none of this is here, this log 3x equal sign, imagine none of that's there, then this is just called an expression. And all you can do is simplify it or evaluate it. But now we can solve. When we have an equation where we have a left side and a right side, we can move things back and forth and divide everything by 12 or whatever we need to do. First, we're going to use the laws of logs to express it as a single logarithm. So that means if I want this all written as one log of base 3, I'm going to have to bring one thing over to the other side. But it says each side as a single logarithm. So I don't need to put it all together. I can leave this one here and leave this one here. If it said bring it all together as a single logarithm, I'd have to bring it over. But it says each side as a single one, so I can leave this side alone. So my next line will be, so I'm going to leave this line. Again, if it said to express it all as a single logarithm, I'd have to put a 0 here, and I would bring everything over. But the question specifically says each side, so let's do what it says here. I've got log base 3 of x equals, let's get this exponent up, log base 3 of 36 to the power of 1/2 plus, now this middle one, there's nothing that I can change here, and whoops, base 3 minus, and the last one, nothing I can change here. So each side, this one is already done. The left side is already expressed as a single logarithm. The right side is not. The first thing I want to do though is this 36 to the 1/2. 36 to the power of 1/2 is 6. So I've got log base 3 of 6, and the rest of it, I can't do anything else here, so I'm just rewriting these parts here. Log base 3 of 2. Okay, writing it out again. Log base 3 of x equals. Now I can put it all with one log base of 3. Log base 3. My first inputs are a 6 and an 18, and they're going to be multiplied. 6 times 18, and my last one is a 2, and that's a division because of the subtraction sign. Log base 3 of x equals log base 3 of what? 6. What's 6 times 18 divided by 2? It's 54. Now I can see the benefit to writing it the way I did on each side, because now I have x kind of isolated here, which is important. Whenever you're solving, you'll always want to isolate x. And if I had brought it over right here, if I had taken this and brought it over to this side, then I would have mixed it all in with all this stuff here. I would have had this minus log base 3 of x, and then I would also be dividing by 2x here, and it wouldn't really be helpful. So I've got my x isolated. So I can see if log base 3 of x is equal to log base 3 of 54, the word log is the same in both, the base of 3 is the same in both, so x must be 54. Therefore, x equals 54, and that is solved. I have the value of x solved there. I didn't do a proof MHF4U of the quotient law, because that does come up in your homework, and there is a whole explanation of the quotient law of logarithms there. So why are we able to divide when we have subtraction? Well, there's a whole proof for that, like the two that we did. We did the product law and we did the power law, but there's also the quotient law. So there's the three laws. Now, why use logs anyway? What's the point of all this? Well, there's one really useful application. This picture I took from your textbook. It is obviously a road that's been cracked by an earthquake. The Richter scale measures earthquake intensity. I hope you've heard of the Richter scale. It uses an exponential scale to measure Richter magnitude versus equivalent kilograms of TNT. So that's how we're getting a scale for this. It's the equivalent kilograms of TNT is how they're measuring the magnitude of an earthquake, the intensity of an earthquake. In order to determine the Richter magnitude number for an earthquake, when the blast intensity is known, scientists use logarithms because it's the inverse operation of the exponential function. So you'll do questions like this in your homework where the scientists have an answer in exponential form, but the unknown is the exponent. The power is an x, and in order to figure out what that power is, what that exponent is, they have to use logs to get at it. So that is your lesson on the laws of logarithms, kind of a bit more of a cerebral one because we had these proofs, so there's some definite theory in there. It's a good one to go over again to make sure you understand.